So hi everyone, I'd like to thank everyone who's joining us today. Welcome to today's CNCF webinar, Cloud Infrastructure for Network Functions, Requirements, and Testing. I'm Christy Tan, Marketing Communications Manager here at CNCF. I'll be moderating today's webinar. We would like to welcome our presenters today, Donna Nehama, Director, Product Management Network Cloud at Intel, and Petar Torre, Principal Engineer at Intel Corporation. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webpage at cncf.io/webinars. With that, I'll hand it over to Donna and Petar to kick off today's presentation. Take it away.
Okay, it's Donna Nehama here. Thank you, Christy, and good morning, good afternoon, and as Christy say, good evening, wherever you are, everyone. So as mentioned in the previous slide I was sharing, Petar and I are here to discuss with you the cloud native requirements and testing activities that Intel has been driving with partners and with the CNCF community over, I would say, over past few years. To set the stage here for our conversation, I would like first to indicate 4 business goals that are driving operators and modern network transformation. You can see them here on the slide. The first goal is the need to introduce new business models, services, and innovation rapidly, and really the emphasis on rapidly. The second goal, and supporting the first goal, is the need for operation agility. The need for a flexible operation that allows a rapid introduction of opportunities and the ability to try, fail fast, and try again. Next, third one here is the resource efficiency, platform selection, standardization, effective resource utilization, and scalability that improves the TCO. And last but not least is to improve end user experience and to make sure we meet service level, or operators can meet service level expectation. We see cloud native as an approach which can support those business goals and can enable operators really move fast and bring innovation with the increased operation efficiency as defined by those business goals. In the presentation today, we will discuss how this can be done. Also, wanted to indicate a comment here that very similar business goals were also set for NFV about 8 years ago. We think that while NFV deployments are ramping, building on the industry expertise plus the adoption of cloud native technologies will really accelerate achieving those business goals that we just indicated. So now let's move to the discussion about cloud native. What does it really mean? CNCF, we are all familiar with the definitions of CNCF, and CNCF has defined cloud native and the approach needed to build dynamic, modern cloud environments. So aligned with the CNCF definition, we have identified 3 foundational elements and also a set of up-level principles to be applied across those elements. With this in mind, with those 3 building blocks and those principles being applied across the 3 elements, we believe that solid cloud native networks can be built. So the first element here is the cloud native application. talking about application that can be of any type. It can be web application, can be network application. However, the common denominator for all is that those cloud native applications need to follow cloud native principles, such as being portable, stateless, resilience, decomposed with using microservices, and there are more definitions of those application you know, the application principles or attributes. The second element here is the infrastructure. We need a foundational, solid infrastructure that facilitates the delivery of these cloud native applications. And the third element is the adoption of lifecycle management principles that enable automation and rapid service introduction. So the principles on the right-hand side of the screen are kind of up-leveled, I will call them, principles that we came up with. I will review it really quickly because it's foundational also for the rest of the discussions moving forward. First one, automation. Automation should be applied throughout the entire application and service life cycle phases. For example, uses of automated provisioning tools, automation of dynamic workload placement, auto remediation using orchestration and IA and machine learning tools. The second principle or attribute here is about cloud scalability. We want one example will be application ability to scale out through the cloud to enable good enough performance. Same principle can be used for failover purposes. Disaggregation, what does it mean? Disaggregation of application and platform components. For example, applications to run independently of each other anywhere on the cloud or on any hardware or on any cloud infrastructure. Hardware abstraction, very much related also to disaggregation, is the ability to design loosely coupled systems. This is something which is out of the definition of an important piece of out of the definitions of cloud native by the CNCF. Application need to be independent from the underlying hardware while enabling best use of the hardware capabilities to achieve the KPIs needed. Resilience is about predictability leading to desired service quality levels. Decomposition is mainly about the application being designed to use containers and microservices as a delivery mechanism. And at the bottom here, continuous integration, continuous and agile delivery, and continuous deployment. So we'll see those implementing those principles across all these, across our building blocks, these building blocks. And here is an actual example of how adoption of the cloud native principles actually help us obtain our goal to introduce rapid innovation and service velocity. So on the first in mind is the application. So from an application perspective, we are discussing here the decomposition, the fact that applications are evolving toward microservices architecture, which means that they are now decomposed into small building blocks, and those microservices are packaged into containers and typically orchestrated with Kubernetes, which we see as the kind of the leading resource orchestration mechanism. Now we have the application really decomposed and moving toward the operation stage of lifecycle automation. Now the applications can be dynamically managed in the cloud. The application lifecycle management process is based on continuous integration, continuous delivery, and continuous deployment approach. And the fact that applications are now broken, I would say, into microservices, into those smaller Lego blocks, makes the software upgrade and update process fast and easy to test and manage. So now, frequent daily production changes are made possible. We can really move much faster. Bottom line is, this is one example showing how this approach help drive our goals, and there are many more things that we can, have a further discussion about. Then next slide here is, I'm going back to our foundational tree building blocks, but trying to emphasize here that applications can be of many kind of application. You can have enterprise cloud application, and we can have network functions. Network function, in particular data plane application, demand performance, reliable, and predictability. And those traditionally are not needed in web application. For this reason, the attributes, and you can see that I added another attribute, which is kind of needed when we are moving to support also network applications. The next slide here is to demonstrate why specific attention should be given to network workload or network function. And the main reason is that there is no one size that fits all. So if you look at those pyramids and the kind of the view of the network, end-to-end view of the network, from the left side on-premise edge deployment to the very right side where we have enterprise and cloud data center, you see that a lot of things are changing. The hardware form factor at the bottom is a different one, which dictate also different power requirements. There are many things that have to do with that are impacted through these different form factor needed. The number of sites across the network is changing dramatically. On the on-prem, we can have hundreds of sites, and mainly smaller sites. And as we move to the right, to the center, there are very few sites and much larger. Same in terms of the requirements. The requirements in terms of latency requirements and performance requirements that are changing across the different slices or the different parts of the network. And in the center here, I've indicated or listed multiple type of workload. Those workloads here are, all of them are, I will call them network functions. Some of them are more demanding, more type of what we called user plane or data plane type of workload, such as the VBNG, the UPF, CMTS, the EPC. All those are having a harsh performance requirements. And while some other workloads, such as, I don't know, the Mac or the IMS, having a less restricted, those are more of what we call control plane type of workload. So with this variety of workload and conditions across the network demand special attention, while still being committed to the cloud native principles. So we still want to make sure that we are addressing the principles that we indicated earlier, such as the hardware abstraction, the composition of the applications, etc. But now things are kind of, I would say, more challenging, and this is what where we are at now, resolving those specific different requirements across the network. And I will now bring two examples. The first example here is an example looking into the data plane application. That's one example out of many. Our goal here to achieve the performance needed by the data plane network application in the cloud native environment. And practically this requires finding a sweet spot between performance and flexibility. The diagram here show how IO interfaces get packets to and from the application. While if you look at the today box, the one on the left, we see here that today we have type of hardware virtual interfaces such as SRV that get us the best performance, and those are driving packets into the data plane in the best way. However, this is more of a fixed solution which creates dependency on the hardware. For this reason, what we call here virtualize, the virtualized IO were introduced, those like VirtIO or VM XNet from VMware. Those virtualized IO bring the flexibility needed, but on the other hand, it comes on the price of flexibility. The new thing introduced, and to balance between performance and flexibility, we added support for AFXDP. AFXDP makes use of the standard kernel. It bypasses completely the software stack, so it can get direct access to the socket. It is supported by kernel today, and as we speak, improvements are being made in order to kind of get the best performance possible, while still we have the ability to the flexibility that we are looking at. So this is one example on the data plane, one type of development to drive innovation and to bring the balance needed. The second example here is an example from the Kubernetes work. This is about what kind of changes were introduced into Kubernetes networking across past year. And you can see here that technology gaps existed in Kubernetes because originally Kubernetes was designed and developed in order to support more of the web enterprise type of application. And with networking, as I discussed so far, you have all these other performance and other things that are requested. So the first thing, and many of you, I hope, heard about, the first thing that was introduced into Kubernetes is Multus, the need to support multiple network interfaces in Kubernetes, something that was not existing. As we introduced Multus, we were able to start introducing multiple different other type of interfaces, mostly done through the use of CNIs. Okay, of CNI interfaces. So Multus is this Uber father CNI interface, and it enables the ability to support multiple of other interfaces. So this is where they come here under packet processing and the efforts that we were making in order to improve packet processing and performance. You can see the DPDK user space CNI, the ability to support SRIOV also in Kubernetes in order to enhance north-south type of traffic. Kubro VN was just recently added as a support for a OVS DPDK when OVS DPDK is being introduced, supporting Kubernetes for FXDP that I just mentioned before, Bond API in order to enable a high availability. Those are all under packet processing. In addition to this, there are multiple resources under the category of resource management. In the past, you may have heard enhanced platform awareness type of capabilities. And I will indicate two important ones here. One is the support for CPU pinning, and there are two open source approaches here. One is CMK, the other one is an approach for CPU pinning and isolation, which is available as part of native Kubernetes. All those enable creation of pods, of different core pods, where the application can be actually assigned on you know, with priority on the preferred cores. So this is another example, and you know, this really required, that's a long list with a lot of there is a lot to discuss here. Also, but you know, also I will indicate one more, which is support for telemetry and for usage of telemetry, and in order to do a better placement of the workload. This is happening under telemetry aware scheduling. So there is much more to discuss about all these improvements in Kubernetes. There is here a link which is called the Experience Kit. In these links you may find detailed information, documentation, which is describing each of those capabilities, how they can be used, and what is the value that they can bring to a deployed cloud native implementation, which is supporting network functions. And I don't want also to miss on the right-hand side here, the lifecycle management. There are multiple developments done to support, for example, Metal Cube for the provisioning stage, and also different deployments with operators and support for operator for most of the features and functions being introduced in order to enable not only the day 0, but also day 0 to day 2 type of deployments. I will skip this one. All these those details are mentioned in the collateral that I indicated the link to, and I want to emphasize the fact that everything we are discussing here is open source. Everything is available either as part of Kubernetes or as part of Intel GitHub or other sites. So no work here is proprietary, and it's all driven with the community. The last piece here that I want to indicate is that after doing all these developments, as I mentioned before, we are pulling together a reference implementation which is taking all the innovation done on top of the Intel assets and resources, the Intel CPU, FPGAs, and the NIC cards, etc. We provide an installation playbook, which is using Ansible scripts, operators, Helm chart, and the KubeSpray for some of the Kubernetes specific feature. We bring it all together as a recommended validated bare metal container, bare metal reference architecture, which can support multiple type of network options. And here is, again, I mentioned the community, and this is the work done in the community, both in the CNCF community and CNTT. I mentioned here CNTT, and I'm going to hand over to Petar here, and he's going to talk a little bit more about the best practice activities in order to drive this into the market. Petar, please take over.
Okay, thank you, Dana. So, like Dana explained, we are on the topic now for multiple years, and what I will cover here in this second half of the webinar is summary of learnings and some practical work that happened in customer projects or in key communities. And this will be with focus on communications, like comms vertical. There is also relevance in other verticals, like in finance, we also see a number of these type of enhancements in Kubernetes needed. What we have here now is looking at what the target is of having those ideal incremental revenue streams and agile services and all that. So to get to that, the idea is to create those services from applications from different domains. So those can be like for NFV or IoT or any of the video topics, analytics and so on, running on the shared common platform. So the platform built at different locations out of different ingredients is exposing itself as one common platform to different applications so that onboarding happens once, and we can build services that are cross-domain for those different applications. While we do that, we need to be very conscious of layers of separations here, and those are the infrastructure, application, and services, both on the functionality side of things on the right, like on the management layers, so that we do not unconsciously or consciously try to couple those, because then there is, of course, impact, and there we know how things went in NFV when it comes to VNF onboarding being a major challenge over there. In pretty much all of these slides, I will explain the concepts and give a summary, and then there is always somewhere a little link with different white papers for further studying or that explains the concept in more details, or there is up to the levels of code that simply can be run in commands. So if you move to the next slide, please. So to instantiate this type of environments, we will, in particular, when we, let's say, focus on some of the very relevant topics in the telco vertical, so it's 5G core and all the vendor offering is containerized, and UPF is like the primary data plane function over there. So when we want to instantiate that and really be certain that both the platform and the function are really working well, according to all the principles that Dana explained at the beginning of the webinar, we have different steps to accomplish. So, of course, there is, this is layered stack, and learning from many projects for many years now is that we need to go and start from the bottom of this stack, building up, and this is the way how the stack is built, and eventually how we can ensure everything up to full automation. And it starts with having the platform functionality checked. Then we also check the platform performance. Then we check the function like CNF functionality and performance. And there is this last step that I'll touch in a second on the cloud resilience levels. So to check the platform functionality, so if you go, still go one slide back, please, Dana. To the table, yes, thank you. So to check this functionality, the enhancements that Vanna was explaining, all this needs to be validated because, for example, all these CNF data plane functions like 5G core ones, an example in the category here, they are based on DPDK. So we will need huge pages, some compliant interfaces and multos and so on. So it's a lot of little features that is worth having good automation tool to check on every node of the cluster if this thing is properly configured. Once it's configured, we do have also tools that can bounce packet traffic between different pods, and I'll explain that in next slide. So that way we ensure the platform is both from this perspective of data plane performance targets, functionally properly configured, and it can handle a certain amount of packets. The step one is to put some CNF, so cloud native network function on top of it, and first check the functionality. There is really good team and progress made in CNCF community that is called the CNF conformance program. And this is, for example, testing how much towards cloud native is particular CNF currently. It is checking for, does it properly scale out and scale in? It should not have static IPs, it should not have privileged containers, and whatever of these little details that are super useful to have are now fully automated there. And currently there is a big effort of testing with broader community, and then there is going to be further work within that, with the idea that that particular line of testing is really mapped into this CNF conformance program. So after that, once we validate that CNF is functional the way how we like to see it in cloud native world, one can really take proper tools for performance characterization of CNF, so create session, put the load into them. And the last step here that is mentioned is about cloud resilience, meaning that the functions can run in shared cloud platforms that will have different impairments. And impairments can be on how the packet processing is going in the networking subsystem, for example, delays and drops and so on. And the other one is on CPU cycles, simply if at some point in time the workloads that are not the most sensitive ones, but we will figure out how to really run it without properly separating them, this would then fit into this category of resilience. Now, if you move to the next slide, this explains once we validated that the platform has the minimum prerequisites to run DPDK applications, which in this case here is huge pages and some interfaces that DPDK supports. We do have a tool that is called procs that can be used as an engine that will change behavior depending on the configuration given. And here we instantiate one pod as generator, another pod as swap, and generator then at the target rate of how many packets it should send, it starts doing that. Swap is sending it back, and then on the generator we can observe how many packets came with which latencies, and can determine the drop rates and latency percentiles. And there is not just these two engines, there is a full automation in terms of Python scripting that here is called Run Rapid, where we can define where these pods are running in the cluster, so we can run it on purpose in different data centers and different racks in the same data center, even on the same server on the same Nehama node if we really wish so. So this way we can go and really get the characterization sorted for the platform from perspective of the CNF. So it's not external load generator, hardware, professional equipment blasting into the cluster and then something is sending the traffic back. We can also see it from inside the cluster, what the CNF, like this 5G core UPF or something, would actually really experience by running at that same spot on the node. So this is the same tooling that we have here now containerized. We have the same engine packaged in VMs and used in open source, in OpenStack world. And this is how we, over the years, matured it, upstreamed into OPNFV, and in the meantime, containerized and also made it send metrics into Prometheus push gateways so that we can more easily actually see what's happening over multiple runs. And this is an example of the paper that if you have the target environment configured correctly, like maybe using those bare metal reference architecture with all this deployment automation that Dana was explaining, literally reading the document and following the steps, we'll get this type of testing for performance characterization established without really, asking our support or so on. This is really well documented, everything. If you move to next slide. So this was what we developed so far before we really started onboarding functions on. Now, the big challenge we had in general with years of NFV was that fragmentation was appearing in many different layers. The major community today that is looking at how to stop the combinatorics and all these different options by agreeing on limited set of hardware profiles, and is really super sensitive on what is cloud infrastructure and what is the application tenant bringing on top, is CNTT, which current name stands for Cloud Infrastructure Telco Task Force. And this is all under joint sponsorship of Linux Foundation and GSMA, led by communication service providers with the major comms vendors included in there. The artifacts that are being worked over there include reference model, which is rather abstract set of design principles and those profiles I mentioned. Then those principles are implemented in reference architectures, which is pretty much requirements. There is on one side for OpenStack, on the other side for Kubernetes, and based on that is normally under umbrella of OPNFV, there are reference implementations, very mature one. I mean, overall, there is more maturity in this whole community on OpenStack because we started earlier, and now Kubernetes is really ramping fast. And then there is reference conformance as a list of test suites that will confirm that every requirement that was written in this reference architecture is actually implemented correctly by the vendors. So reference implementation primarily is used to build this conformance test suite that one can go and run versus vendor implementations of NFVI and VNFs and CNFs. So this is very big community with critical mass of the operators. And if you move to the next slide, this is of course then the reason why we are active there. And this bare metal reference architecture that Dan explained and all this testing that I was mentioning, this is what we are listening to the requirements coming out of reference architecture for Kubernetes, which is RA2. And we propose from Intel, and already through our investment in OPNFV, some of the pods over there are being installed with this reference architecture to be CNTT reference implementation, one of the two examples that are being currently proposed and invested in. And as part of the testing suites, we are then contributing the tools that I was mentioning, primarily those for performance characterization, and then when we mature those for functionality, then we will figure out what to do with those. So this is, of course, a lot of engineering work, and we are pretty proud to be able to be active member of the community and really contribute all this. So this was a number of things that are platform related. So now when we looked at what does it take to onboard something on it, and keeping in account learnings from many years of NFV, especially the target that is written here of service agility and easy operations. We are super sensitive on properly decoupling applications from the infrastructure, other platform services, and also applications from other application components. And here on the left side is a little summary of that. So there is hardware infrastructure, software platform, and this is what the cloud infrastructure provider brings. And then there is what tenant brings, is the application functionality and the application control. And then I talked about this decomposed a little bit. So where possible, of course, there is huge benefits when things are in microservices. And this is here on the number 4, because then we can have upgrades done more easily. The failover overhead is lower, and there are other benefits to that. This is still, I mean, this is relevant for sizing and operations. What is really critical to achieve this decoupling of the application is to be very conscious about how much is application coupled or decoupled from the infrastructure. And here we, of course, have this example of SRIOV that in current implementation does have hardware driver in the application. It's a trade-off that in many cases was accepted because that's how we get to performance, but of course that's not ideal. And then in CNCF world, this is properly captured as exception, and there is the whole exception policy framework around it in terms of how to improve this situation. So that's number one, infrastructure is very well understood. The platform services are all the other functionalities of the platform itself that is not the application, that are repeating, and even to build a basic Kubernetes cluster, there will be other CNCF projects included. To build any network functionality, typically there will be also load balancers and data stores for state, and we will have to collect the metrics and do the logging, and so many other things are needed. So there is less awareness of dependency of the application towards this type of platform services, and this is something that there are discussions in few communities trying to figure out if we can agree on what is the preferred way for this common functionality in terms of which project and how to really use it, trying to avoid the fragmentation that can come in the system when a lot of vendors are bringing their own version for collecting metrics, like maybe Prometheus and the way how they use it, and all of this will then have impact on the integration side. Number 3 here is about the application resiliency to the impairments of cloud platforms that I briefly mentioned before. This is when in the past the application itself did not have to be resilient because the platform was carrier grade, and now when we try to decouple those, yes, we still need to, because of non-resilient applications, we have a lot of requirements on the platform, and this pretty much creates a lot of little coupling points. So to really also decouple that part, we will have to address this resilience by addressing applications accordingly and testing it accordingly. So for that, also we will have to work, and we already work on some of the SDKs, and we'll see how this thing goes. There are technical, economical boundaries in everything that we do, and not just ourselves, but the whole industry in terms of what is technically feasible and how much are we all willing to invest into it. So infrastructure is well understood, platform services less, and then the resiliency as concept we first have to grasp and work on it. If we move to next slide, please. So few practical examples of what we did. So we are not just inventing theories. This is example of decoupled stack, and what we were proving here is how do we have the software platform with all the required intelligence that is needed to handle hardware acceleration, like Intel QuickAssist technology here, which is accelerator fixed function for both encryption and compression algorithms. So how do we build a platform that knows what this accelerator is, can perfectly well assign it to the pods that are scheduled, and when the pod is deleted, take all these resources like virtual functions in this case that are handled by this device plugin for QuickAssist back into the pool. Node feature discovery is exposing the label so that we can recognize on which node such a device is present. And the exercise was how can we keep this intelligence in the platform as much as possible and do not expose details that are not wished really in application, because then we need to do the enablement and more difficult onboarding and even further up in the orchestration. So what we did here is have the platform where this device plugin for for Quick Assist is handling the accelerator, node feature discovery exposing the label, and then we have the blueprint that says for this proper policy-driven orchestration of CLOUDIFY, this Tosca blueprint that has preference for the node that will have Quick Assist, because when we place Nginx properly enabled for Quick Assist, then this thing will look underneath. If it sees the device, it does have a configuration and it does have the appropriate drivers to use it. If it does not see the device, it will simply run on CPU cycles. And then this is one container in the pod, and the other 3 containers are Apache Bench that are pretty much doing this HTTPS load. And what the paper linked here explains is how this whole thing is configured. The label exposed on the Kubernetes level is only one string. How the whole pod is constructed is explained over there with the source files, and there is also some recommendation for further work, because if this is normally for volume reasons, this is dual socket server, so then we would have 2 NUMA nodes. Enabling topology manager would help find where exactly this type of adapter is, and this was on purpose done with Quick Assist being fixed function accelerator and with Nginx, because there is an open source version of that, so that we can go and publish the whole thing in open source and really share the examples. And now when we need to do this thing for deployments that have this programmable acceleration card, which is adapter with FPGA, the difference here is that the blueprint in terms of workflow, before the whole thing starts getting used, will have to load the image, so RTL, onto the FPGA. The rest of the workflow and the rest of the logic with node feature discovery and device plugin for FPGA, the rest stays. So that's an example of that. If we move to next slide, this one is to focus on performance. So again, we have very similar platform using, in this case, is again dual socket Intel Xeon 2nd generation Gold family there, and one of the Ethernet adapters, and there the whole software platform, like Dana was explaining, this bare metal reference architecture. On top of it, we did put AS3, which is the research institute in Hong Kong that have representative EPC and 5G core stack, and UPF component was put on top of it, and 4 units of height, we run 1.3 terabits of traffic. So that's an example of how this whole thing can be configured for really high throughput. This is doable with other types of use cases, and this engine that I explained before can validate that the platform is ready for that. And this is just a little reminder, this is not to expect that now the usual UPF with all the functionalities and features needed for deployment would see this type of number. That's not what we are claiming here. But just that the platform with the right enhancements properly configured in hardware and software can execute this type of very representative workloads and use cases. If you move on. So with that, we covered a lot of how to build the stack, a number of examples of how to really come to agility and performance. So this is, of course, needed, the whole technology and adoption of that. Still, learning from many projects is that actually the success rate, the depth and speed of such transformations on beyond technology is defined by widely adopted design principles, understanding that organizationally this needs to change from what is typical in telco vertical is management of silos into management of layers, organization, and how the people are measured and how they are skilled, and all that also needs to change. So it's not just a technical stack that somebody simply adopts. How hard to change each of those is visualized here on the right side. So everybody would like to have better external outcomes. They are direct results of the processes embedded in the organizations. And in those organizations, people behave according to the reward system. Sometimes reorgs happen without changing the reward system, so there is no fundamental change in behavior. And when the reward system is stable for quite some time, then this defines what is the culture and default mindset. And here the arrow just shows how hard it is to change, but this is simply to reflect on what needs to be done beyond just adopting Kubernetes enhancements and the right hardware and software stacks. If you move to the next slide. So this is just a little summary. We are at the end here. We'll answer a couple of questions. So this approach for the application development of cloud native is what is really needed for the current marketplace and competitiveness in services. This is both based on these technologies, and that way we achieve the service velocity. That should be the major and primary target in all this. And from Intel side, we invested early, filled those gaps, and we will continue working to enable this flexible, agile, and performant type of environments. Last slide here only has a couple of if you move on to the last slide. Yeah, this is some of these links that are maybe more important than the others. Some are repeating. So to learn more, you can look at the first one. This is this container experience kit that includes all the explanations about how to construct Kubernetes cluster for sensitive workloads like data plane. There we have all the documentation about all the individual features plus the whole reference architecture together. And then there are some other links that explain how to do this for 5G core, UPF example with AS3, and we do have all of that recorded as trainings, a little training videos about each individual feature, or full Intel Network Academy list of trainings on how to think and grasp this whole transformation from basics of what is virtualization in cloud to details of different versions of one or the other software needed. With that, I'm done. So beyond this, we'll answer here a couple of questions. Anything else, please go to your Intel representative, and we are, of course, very happy to work this thing with ecosystem for joint wins at the end customers for their benefits. Couple of questions. So I see here one that says, may I ask what 5G reference this is here? So now I lost which slide it was. So on UPF, there was this, of course, AS3. The example with the programmable accelerator is used in 5G virtualized radio access deployments. And those are the two that we pretty much covered here. Both of those are very new category of use cases that is, of course, then done with current software designs, which defaults into containerized applications and Kubernetes as needed. So
oh, sorry, go ahead.
Yeah, I see here another one. So what areas are worked on, bare metal, others? I don't see here comments from attendees. Okay, so there is a question. Let's take this one instead of me trying to invent question and answers. So thanks, Jindong. So containerized 5G core, Intel specific. No, we don't have Intel products for 5G core. we are happily working with a long list of ecosystem partners that includes the major ones, starting from Ericsson, Cisco, Mavenir, Nokia, to more disruptive ones like Affirmed. And sorry, of course I missed somebody, but after half an hour of talking, I might be excused for that. But we do not have intentions to bring our own VNF, CNF product out. We will take all our assets and knowledge and work to enable the ecosystem that is bringing those functions. With that, I think we are closing to the end of this webinar.
Thank you again, Donna and Petar, for your presentation today. Yeah, that's all the time we have for today. Just a reminder that the webinar recording and slides will be available later today on the CNCF webinars page. We look forward to seeing you at a future CNCF webinar, and have a great day, everyone. Thanks again.
Thank you.